In this last video introducing concepts of potential energy among interacting particles, we will talk about a more realistic approach when you have more than one electron in atoms. We have said, and let's remember, that the closer the distance, so the lower the distance, the higher the attraction, and the lower the energy and the higher the stability. In other words, this will also change the ionization energy. Ionization energy will be larger. Distance changes the attraction, the energy, stability, but also the charge of the nucleus. So the higher the charge, we will use Z to express the charge of the nucleus. The higher the charge an electron feels, the higher the attraction, the lower the energy, etc., etc. So let's look at helium, for example. The energy of helium 1s. Now we know why this is negative. And here we're comparing the energy of helium 1s with the helium, so helium plus and helium 0. That means there's two electrons. Now something is happening here. These two electrons repel each other. And if they repel each other, it means that this electron is less stable because they do not feel only the attraction with the 2+ nucleus, they also feel the repulsion with the other electron. This is why this electron in helium 0 is less stable. However, when you only have one electron in helium plus, right? Helium has only two electrons. The moment you make a cation, it's because you remove one electron. There is no shielding. In other words, there is no repulsion among electrons. This electron feels all the 2+ charge of the nucleus. All right. So we just introduced the concept that we call shielding, or if you will, how electrons bother each other so that they screen the charge of the nucleus. This means that if electrons kind of repel each other and they screen the charge of the nucleus, instead of considering the charge, what we will use is the effective nuclear charge. The effective nuclear charge that I represent with ZF is the actual charge that electrons feel if you consider the repulsion with the other electrons. In this case, for example, if you consider lithium, this electron in here is less stable now than if these two electrons were not there. Okay, we will say that the effective nuclear charge now, from this electron point of view, is as if it were only +1, because these two negative charges are repelling this other electron. Okay, so two concepts: shielding and effective nuclear charge. The higher the shielding with the other electrons, it means that that electron does not feel the actual charge, but a lower charge that we will call the effective nuclear charge. Okay, so you could think of using these kind of graphs that we've been using so far, that when you remove an electron from beryllium, remember beryllium neutral is 1s2, 2s2, you have two electrons in the 2s orbital that kind of bother each other. That means they are less stable than if there's just one electron here alone that does not shield. Okay, so we will say that the 2s orbital has a higher effective nuclear charge because there is not an additional electron that repels with the other electrons. So this one will have an effective nuclear charge. The effective nuclear charge is characteristic of a specific electron in a specific orbital. Okay. Still, this 2s orbital will not feel the full. Again, beryllium will have a 4+. It will not feel the full 4+ because there will be two electrons in here in the 1s orbital shielding a little bit. So definitely the electrons in B2+ would have a lower energy. All right. So let's just run a very, if you will, a simple set of questions. I kind of implicitly said that, but let me say that again. Typically, inner electrons will shield -1. This means that when we build beryllium and we said, well, the beryllium will have a 4+ in here, and here you have the 2 electrons from the 1s, and here you have the 2s. You can say that the electrons from the 1s completely remove the additional charge from the nucleus. So what is or let me give you another example since it's already here. We're talking about lithium. Lithium has a charge of +3. So what is the effective nuclear charge of the lithium in the electron on the 2s? Well, the effective nuclear charge will be the 3 protons that lithium nucleus have minus the 2 negative charges from the 1s. So you could say that lithium in the 2s electron in lithium feels an effective nuclear charge of 1 because the electrons in the 1s screen, at least with 2 charges, the actual charge of the nucleus. All right. Electrons in the same shell, however, they will shield less than -1. So it's usually a fraction, maybe 0.5, depending on the kind of orbital. Okay, but definitely, of course, the more electrons, the more the shielding will be. So let's see if we are able to answer these questions. So for an atom of oxygen, the electrons in the 2s, being closer to the nucleus, perceive a higher or lower effective nuclear charge than the electrons in the 2p. And that's important. If the 2s are closer, that means they are lower in energy. They will be able, so the 2p electrons will have a screen from the 2s and the 1s because they are closer. However, the 2s electrons will only perceive the screening from the 1s because 1s is the only one that is closer. So in this case, they will perceive a higher nuclear charge because electrons in the 2s are only screened by the 1s. Next question, the shielding felt by electrons in the 2p, will it be higher or lower than the shielding felt by electrons in the 2p of carbon? Well, how many electrons do we have in oxygen? We have the same, so both carbon and oxygen have the 1s2, 2s2, but oxygen will have a 2p4, however carbon will have a 2p2. 4 electrons bothering each other will have more shielding than 2 electrons bothering each other or repelling each other. All right, so the shielding will be higher. All right, but we know that the effective nuclear charge on the 2p of oxygen is larger than in the 2p carbon. And if you think about this, this means that the 2p electrons in oxygens have to be more strongly attracted than in carbon. Even though they have more shielding, the increasing of charge 2, right, when going from carbon, which is a +6, into an oxygen +8, even though the electrons in the 2p of oxygen have a higher shielding than carbon, that's not enough to compensate the increase of +2 in nuclear charge, so they will be strongly attracted. And there you go. This is why oxygen is more electronegative than carbon, because the factor of increasing the nuclear charge is more remarkable.